Okay, so are we ready to get started? Okay, so Demetrius says yes. Okay, then let me share my screen. If someone has any trouble, please let me know in observing my screen or anything like that. I've made the font a little bigger, so it's more legible. Okay?
Yep.
Okay, great. All right. So I said I'm going to start exactly with you. So I'm basically going to clone the SDL AI workshop Git code onto my login node and onto my home directory, and then I will go through the examples one at a time. So you can follow my lead, or if you have the directory already, you have the repo cloned already, just wait until I get to the part where I'm submitting code. Okay, so now we are here. So let me go into my workshop and the simulation ML directory. So you see I'm at 05 simulation ML, and we want to first start with theta KNL. So we can go into theta KNL. Okay. Over here, like I said earlier, I'd recommend using another screen if possible, or at least half the screen, to keep these instructions open. So if you go to theta KNL, you'll have these instructions for us to run this code. So the first thing we'll want to do is we want to grab an interactive session on theta so that we can run this one at a time, one step at a time. So let's do that. Okay, so let's put this guy in over here, and this might take a little while, but we will grab ourselves an interactive node. For an hour. Maybe this is a good time for me to look at if there were any questions on the Slack channel. Okay, so there was a question. Did I use automatic differentiation for my open form paper? I did not. This was not, there wasn't any automatic differentiation over there. Okay, what else was there? Let's see. In simulation, sometimes you want to measure the statistical errors. If the machine learning improves the simulations in C2, doesn't it change the statistics as well? How do you measure that? Well, I mean, that's a very, very good question. It's difficult to say a priori how your ML might perturb your simulation. The example that we have over here is kind of not a very invasive method of using machine learning in simulations. We run the simulation and we use a machine learning model to approximate it. But there are some situations where your ML is asked to perturb the solution in order to accelerate it, or with the with the ostensible motivation of making it more accurate. So it's a difficult question to answer. The interplay of simulation and ML, especially if your simulation is coming from, say, a partial differential equation in terms of numerical stability, accuracy, convergence, etc. These are open questions. So that's a good question. Okay. And I think that was it. And on cue, we have our interactive session that's open. So feel free to use the chat if you're having any trouble getting onto these interactive nodes, or use Slack, sorry. All right, so now we have an interactive node. Again, let's just follow the instructions on the GitHub README. And so the second instruction is source setup.sh. So again, let's just look at what setup.sh was. I went through this. So this is just going to run Cmake for us after adding the requisite stuff onto our Python paths and our LD library paths, right? And it's also going to clean up some of the junk before, so that whatever results we get are ours and not previously from the repository. Okay, so let's source this guy. Oops, not in the right directory, because when we logged into the interactive node, we were sent back to the home directory. Sorry about that. So we can rectify that quickly. So we are here. There should be a source directory over here. So let's source this. Okay. It's going to use this Intel C compiler. All this is available by default when you log into Theta. I did not load any special modules or anything before starting this. And if you're ahead of me, if you grabbed an interactive node ahead of me, feel free to go and try out the following steps, okay? Also ask questions whenever. Okay, so standard Cmake boilerplate outputs. Okay, so it looks like it was able to build and link properly. So our app is ready. So just to mention, we started our building on the Theta KNL directory, but within the source, within the setup.sh script, it actually changes the directory and puts us into the build directory. So now within this build directory, you will see our executable that's been built, app, excuse me. And also these files are already there from previously. We'll be needing them. Nothing has happened to these two files, and this is the new information. So previously we had some PNG files, some Numpy files, which were from our tests to make sure this runs. And that has obviously been deleted so that we have our own results. And then we can go in and just run this code directly using app run. So app run is to be used in Theta over here. So what this command is saying is that we will use one node and only one process on that node. So there's essentially a serial code with a certain number of OMP threads and some instructions that I won't go into now. But depending on your C++ executable, you will probably have your own combinations for these that will basically optimize your performance. Anyhow, we run this code now, and let's see what happens. Okay, we will be spitting out some information to standard output. So for example, over here it says initializing Numpy library. Okay, where did that happen? Let's go back and take a look. So the initializing Numpy, so we have to go to our C++ file. So the initializing Numpy library happened here. That means our Python initialization was successful. What else after that? So it loaded our Python module, which was here, okay. And then it said, now it printed something that was outside from the Python module, from within the Python module. So now where is that happening? So that's not actually being printed out from C++. That is something printed to standard output from Python. So if you go into your Python module.py file, there is a print statement from Python saying from Python with the Python module. So, and we are able to run this code. It ran a little faster than I expected. I suppose I was taking some time to explain this, right? So it loaded the functions from the module, it loaded some functions, and then it was calling this Python function successfully. So let me see where that was happening. Okay, so it loaded the functions, and then from within the collect data function, it was able to call our analysis, our collection function, and then finally it was able to it spits out a certain computer time, and now it's starting our data analysis. And this is something that people who have used TensorFlow will be familiar with. So you can see this is being run on KNL. So there is no GPU over here, but it's using TensorFlow 2. And it's now training a LSTM using the data that we generated from our simulation. And this was run using a C++ executable. So this is something that is, you can think of a lot of possibilities over here. This is essentially how this code works. Any questions at this point? Okay. So perform some inference. It restored the model successfully. It was going to perform some inference, so it restored the model, and now it's making predictions, the test data. So you will see that this will be much faster when you run it on the Theta GPU, which we'll see. But we'll take a look at the results first, okay, in a bit. So while we are waiting, I'd like to show you what results we got from this. So over here, I'm just using Visual Studio to log into Theta remotely. And you can see that it basically generated the same PNG file that you have on the GitHub repository. It hasn't yet generated the time series predictions because it's still working on that over here, as you can see. But it generates the eigenvector that we expect and the field evolution that we expect. Okay, and now it should have also generated those time series profiles. So if we refresh this guy, you can see now that you have these predictions for us, which are not that great. We didn't really want to make this a scientific problem solving sort of session. So the time series has to be improved, obviously. But you can think of how you can take this this idea and how these things work together to deploy them on some of your problems. Okay, so this was Theta KNL. I'll be moving on to Theta GPU after this. So this is a good time for people to make sure that they're following along and they are not confused anywhere or for anything. Okay. Another thing that I want to mention here is if you do go to the Theta KNL subdirectory over here, there is a submit shell script, which actually does this entire thing for us and submits it to a queue. So instead of having to grab an interactive node, you can just submit it to the queue, and so you don't have to wait to grab an interactive node. It just does that automatically. Obviously, if you then get an allocation on our systems and you get some time to run codes like this, you have to put in the right project and the right queue for that. Okay, but I think the SDL workshop allocation will be around for a few days, at least for a few weeks maybe. So you can play around with this. So Theta KNL is relatively easy to work with. Okay, any questions at this time?
Romit?
Yes.
Where in the code is multi-threading used? Because while running the code, you said OMP num threads equals 32.
We haven't explicitly specified multi-threading anywhere in the code. So that was just let's just say that was the default command that we used. We haven't explicitly gone out and tested this for multi-threading and things like that.
Okay, so I was just wondering the purpose of that option.
Yeah, so I can only point you to the documentation that we have online on how to optimally select those parameters. It's definitely application specific, so so you'll have to do a little bit of trial and error, a little bit of profiling to find the right number for that. For the purpose of this presentation, we didn't do that.
Okay, thanks.
Yeah. Okay, so this was theta KNL. Let's make sure we don't hog on to the interactive job. We don't need it anymore. So is anybody having any trouble at this point? Has everyone been able to run this appropriately? I hope so.
This is Jifu. I think I run it into an error. It says there's no target file for make.
No target file for make.
Right. I posed my question in Slack as well.
On the Slack, okay. Okay, so we can deal with it on Slack. Okay, there might be like a specific mistake somewhere that we have to solve. I'll move on to theta GPU. Okay, and we can we have some time. I'm assuming we will finish maybe 15 minutes ahead of time, if not more, so we can help people debug some of their problems. Okay. All right, so now my theta KNL business is done. So I'm going to leave this terminal and good practice to open up a new theta login node. Okay, I'm back in my home directory. And now we want to use our theta GPU subfolder over here with some instructions. So the instructions over here are slightly larger or longer, sorry. And for good reason, but if you follow them, you will not have any trouble. You'll see a pretty dramatic speed up in your compute. Okay, so the first thing we want to do is we want to log into the GPU SN1. Okay, so you SSH into that. So you will still be in your home directory, but now you're on GPU SN1. And you will ask for an interactive session on an A100 GPU. Okay. So over here, the goal will be to ensure that TensorFlow uses the GPU when it's doing the LSTM training. Everything else will be identical, but the GPU training, but the LSTM training will now use the A100. So that is the purpose of running this on theta GPU. And so you can think of how many applications there might be there for a workflow like this on heterogeneous computing, right? So heterogeneous architectures will maybe be when we have some component specialized for classical computations, using CPUs, and then it'll also have access to a bunch of GPUs which you can use for ML workloads. So that's kind of the goal of this example. Okay, so now we've got ourselves a theta GPU, right? So what do we do next? We have to we will have to use Singularity to get access to TensorFlow 2.2 on the theta GPU. This is the unless things have changed, this is probably the safest way to get access to TensorFlow and Python and all these things without having to do any building from source yourself. Okay. Questions about Singularity can be directed to Taylor. He's the guru for Singularity. So, so on my end, I have used this this container that he's made available to us for running TensorFlow 2.2. I think there's a PyTorch version as well. So again, for people who are feeling ambitious, if you want to call PyTorch from that ML module and do something different, you'd have to go and find the PyTorch container, which is available on, if I'm not wrong, theta GPU docs. Yes. So there's this repository that maybe someone can post on the Slack where you have information about these different containers that are available from NVIDIA that are being used for the A100s now. So we have PyTorch and TensorFlow 1 and 2. So I'm using TensorFlow 2. Unless there's any special reason, I don't see any reason to use TensorFlow 1. TensorFlow 2 is way, way, way easier to use. Okay, so we have activated Singularity now. So we have access to TensorFlow. What do we need to do next? Well, we need to first get access to the internet. And the reason we need access to internet is because we have to download some packages. So the Singularity container does not have things like matplotlib, which you will remember we need for visualizing our flow field. So we need to download them in a virtual environment. So we are going to export these. We need access to the internet. So let's just do that. Okay, by pasting these two guys. And once we have access to the internet, we can install a virtual environment that we download these packages to. Okay, so for example, over here, I'm just downloading virtual environment. In my case, it was already there. So maybe that's not necessary. Okay, now this is some place that you need to pay a little bit of attention. Okay. Over here, I am actually exporting a variable that has the location of my virtual environment. In this case, it's my home directory. So you need to change this to reflect your home directory or your path of interest, wherever you want to keep this. Okay. So we want to install our virtual environment over there. And we do that like so. Okay, so again, it's good to have another shell open. So over here, if I go to my home directory, I will see that there is a virtual environment that is now available. Okay, Theta GPU TF environment. We'll be using this for our app. That's available now. And we will now want to activate this environment. So you should see this sort of flag come up in your command prompt. After you have activated that environment, we can now install packages that you'll need over here. Okay, so this basically depends on what you want to do with your Python. So in our case, we only need matplotlib and we need sklearn, scikit-learn. You can install PyTorch if you, well, no, for PyTorch, it's best that you get another container, but you can install like other packages that you might need for your specific example. So let's do that. So I'm going to install Cmake. So Cmake is required for building our app. Okay, so we don't have access to like a Cmake natively when we grab Singularity. So fortunately, Cmake has a Python installation that we can leverage for that. So that's useful. So that solves any problems related to building. And then we will do the same thing with matplotlib for plotting. And so in my case, a lot of this is already cached because I tested it previously. In your case, it will probably be downloading something from the internet. Hopefully people aren't having problems with this. And now I have scikit-learn. Okay, so
Romit?
yes.
Yeah, it looks like some people are running into issues with trying to pip install from within the Singularity container.
Did they activate their virtual environment?
I believe so. I know it's hard to it's definitely hard to try to watch the Zoom, be on Zoom and watch the Slack channel.
Yeah, you might just run through the, just show the commands again, start going up your terminal there.
Sure, yeah, I can just.
One thing that might explain the difference that people are having or observing is that your packages are cached where theirs are not, and so they're having issues with the downloading. So can you clear your cache? I don't know how
to. So are they having trouble downloading? Like does it not download? Okay.
Right.
I think
Yeah, so no, sorry, this is Lander. No problem setting up the virtual environment, but then when doing the pip install Cmake, that's where it gives a problem saying that the version that satisfies the requirement does not exist, or there's no matching distribution.
Did you activate your virtual environment? Is it active?
Yes.
Okay.
Romit, I think you could. I think you could, if you were to try to go back through the Python pip install commands, and if you pass the it's like ignore cache, ignore dash cache.
No cache.
Yeah,
No
okay,
cache.
that's what it is. And that should force you to try to re-download it to see if you run into the same problem.
You have
So
to
this way?
uninstall it. You have to uninstall it first, though.
Okay. Works for me.
Well,
Yes. Did you export the proxies properly, Lander?
Yeah, I just used the same address and port number as the one provided in the README.
Okay. Is anyone else having trouble with the same thing?
Yeah, I'm having the same thing as Lander.
I'm actually, if I remember correctly, the proxy is not set up with
Oh, this is a
an
good point.
HTTPS. So actually for the export with the HTTPS, you just use the plain old HTTP : // So that might be causing trouble.
Okay, interesting.
Can you print your end, Romit?
Sorry?
Can you print your variables, the proxy variables you have?
Yeah, yours is set that way too. So I don't know.
Yes.
You can also try lowercase. I think that pip definitely respects both cased versions of them, but I know the lowercase version is more common in other applications. But I don't think that's the issue here. Looking at the specific error that's being printed out, it seems to be an SSL error, and it's like a broken connection or something. And
So
it keeps retrying, so clearly it can ping out, but it's something with the fetching.
So is it related to downloading? Like, is it related to internet access? Or no, it's not related to internet access then.
I was having the same problem, but making that change on the second export from HTTPS, or yeah, the HTTPS to HTTP seems to have at least resolved the Cmake problem.
Okay, I see. So
Well, don't question it. Let's just do that.
Yeah, that did it for me too. Thank you.
Okay, it doesn't seem to have a problem for me. That's interesting. So, well, this is why you have workshops. So you find these things. Okay, so so for people who have been having problems similar to the ones that we just discussed, I'd recommend exporting your HTTPS proxy to HTTP instead. In fact, you know what? I'm going to go ahead and try it myself. And let's see if I can.
Yeah, it worked for me as well.
Okay, excellent. Yeah, so maybe that might solve your problem. Okay. So shall we move on, or do we need a couple of minutes to iron this out further?
Good to go. Okay,
great. All right, so now we are ready, okay? So this couple of commands, you don't want to execute this. This is just information telling you that later on down the line, as long as you don't delete your virtual environment, you can just source the environment, activate it, and then go on your merry way. So So this is basically one-time stuff that you have to do. Okay, so now we're ready. We'll just do exactly what we did for theta KNL. We will first, we will first go into the right directory. That is important. Okay, so over here we have our setup shell script. So let's take a look at that real quick. It's going to be similar to the well, it's not going to be similar to the KNL one because a lot of the information is already in the path. So we don't need to worry about linking at this point in time. So we can just clean the repository of previously generated PNG files and Numpy files and use Cmake. So we will do that. Much faster. Target app is built. Okay. And now that that is done, we essentially run it with MPI run, not app run anymore. This is MPI run. Okay. We are now inside the build directory. Okay. So again, over here, we just have information related to Cmake, the executable, and these two Python modules. Okay. So if we paste this guy and run it over here, you will see now that we were able to use CUDA from the LSTM and like so, and it's basically doing exactly what was being done on theta KNL, but now using the GPU for the for training the LSTM. So, and you can see it's much faster. Okay, and the speed will get better once you have a bigger ML task to perform. Okay, so we are done with this guy over here. Let's quickly take a look at our results. So now we need to go to theta GPU. So I need to get rid of these guys over here. These are from theta KNL. So we go into the app build of theta GPU, and we have the examples over here. So it's solving the same problem. So you get the same trajectories, same results. So that's nice from within theta GPU. Okay, except now there was a little faster because the LSTM was being trained by the GPU. Okay. All right. So in order to submit whatever you did here on the theta GPU to the queue, it's slightly tricky because it has to go through Singularity. So I have an example for that over here. So you can just use q sub of submit.sh, where submit.sh is this file over here. So over here, we need to submit and give some arguments for Singularity. So the submit uses this is kind of like a workaround that we are using at this point. So we have to give Singularity a script to run from the script. So once you actually q sub this guy over here, you need to go to the q submission.sh file, right? And make sure that you are exporting the right path for your virtual environments, not this anymore. It's what you specify, your home directory, for instance. And of course, activate that virtual environment. And so that's pretty much it for our hands-on. So you just q sub this guy. Another thing is this q submission should have to happen from the theta GPU SN login. So you cannot do it from your home directory. So you need to, if you open theta and you go to theta GPU SN1 over here, you can go to your theta GPU subdirectory within our GitHub repository, and over here you can basically q sub submit.sh. So this will submit a job for us and basically do the exact same thing that we did, which you can see like so, right? So this guy running is my interactive job, and this is the one that I just submitted. Okay, so so that will help automate this process. You don't have to grab an interactive queue all the time. So it's a little more trickier on Theta GPU, but if you follow the steps, it should be fine. Okay, so I'm going to exit my interactive job now because I don't need it anymore. And that leaves us about 20 odd minutes, 20 to 25 minutes for people to make sure that they've wrapped their head around this. And let me know if you have any questions in the Slack, and we can help with that. Does that sound good, Bethany?
Yes, sounds good.
Okay. So anybody still having trouble with getting through these examples, either on KNL or GPU?
I don't think so. It looks like, as far as I can tell in the Slack, it seems like everybody's worked out all of the issues that they were having, I think.
Okay, excellent.
I could be speaking too soon. That might not be the case, but as far as I can tell.
Okay. Would people be interested in me going in and giving them more detail about the Python code that we wrote? I kind of glossed over the LSTM, for example, because it just represents a black box machine learning workload that we are calling from C++. But if people are interested, I can go and just go through the code in a bit more detail. Would that be helpful for people, or do you think you just want to fiddle around with it yourselves and we'll be on standby to help you out?
Could you go into it a little bit? Because I'm curious why actually using the model performed such bad coefficients.
Oh,
yeah.
Or it trained okay.
Yeah, so this is not even close to like a model that performs well, right? So if you actually go to the paper that we linked, we have to run models with information from many initial conditions. We have to train models with information from many initial conditions. We have to build inductive biases into our models. This is just a representation of taking some arbitrary time series data and then training on it, right? So the purpose of those plots that you see right at the end is not to say, oh, we have a model that works. It's just the fact that we can model something. We have to improve it, but that was the motivation. But let me tell you why, for example, it's not working well. Okay.
What about the R squared looks really good, but the figures look really bad. Are the figures up to date?
Yes, and there's a reason for that, right? So so the reason you get good R squares during training and then poor R squares during testing is one of the classic problems of LSTMs. Now, I don't want to go into a bit of a mathematical rant, but the LSTMs don't give you any stability guarantees when you're making forecasts in time, right? So so what we are doing essentially over here is, if you look at the images for the field evolution, right? We are giving it data for a process roughly up to time step 1000. So we're giving it information up to time step 1000 and asking it to forecast from 1000 to 2000. So these are one of the dangerous pitfalls of machine learning being used in an unintelligent way. You cannot use machine learning to do extrapolation. Okay, not to in an arbitrary sense, right? So if I have weather information only for January and February for my training, I cannot predict stuff in April and May. It's just not possible. I will get a prediction, which you are getting here as well, but it's not going to be very good. So it might be good for predicting within those 2 months. So that's the same thing that's happening over here. We are not able to extrapolate, right? Even though we are able to learn what is happening in the first 1000 time steps, because what happens afterwards is just unseen, correct? So ML should always be done and then deployed on data that comes from the same underlying distribution. Okay, so if I, just to give you a dumb example, if I train a classifier between cat images and dog images, right, and then ask it to classify between horses and, I don't know, warthogs or something, you are not going to get a good performance. You'll get something, it'll tell you yes and no, but you don't know whether, but it'll be poor basically. And that's what's happening over here. So to point to the relevant location in the code, if you go into the ML, the Python module, you see what I'm doing over here, right? I'm taking the first half of all my time steps. Actually, I'm not even taking the first half. I'm taking the first quarter of all the information, all right? And I'm giving it the last 3 quarters for testing. And that's the thing. So it's training, it's getting accurate on something that is kind of irrelevant to our ML task, okay? So how would I solve this problem more efficiently? I'd probably reframe the problem in such a way that the ML model depends on the, for example, the frequency of the sinusoid. So I will simulate multiple simulations with different types of sinusoids, and I'll do forecasting on all of them. I'll do training on all of them. And then I will choose a new sinusoid, which I wasn't using in my training, and then try to predict in that. So that's the way that surrogate modeling has proven most successful, right? But at the end of the day, the LSTM does not have these partial differential equation behaviors baked into it. So that's one of the limitations of this. Now there are other methods out there, for example, the physics-informed machine learning stuff that Karnidakis is pushing, or some constrained neural network architectures that other people are pushing. So those do improve your ability to do forecasts because they do build in some hard or soft constraints that are physics relevant. But again, for this application, we do not do that. So that's why you're seeing that performance over there. Does that make sense? Yes, no.
Looks like somebody said in the chat said yes. So
okay. Yes.
Do you want to tell them about PyBind and when you might want to use that?
PyBind. Okay, so so what we used over here for coupling C++ and Python was the Python C API. That's the old-fashioned way to couple it. But there is a open source software that's being developed called PyBind, which makes it a little easier to use it. And specifically the syntax is a lot cleaner, garbage collection, and we had to make sure we were taking care of any references manually. So PyBind helps you do that automatically. PyBind is a lot more valuable for people who, for example, I think they have a lot more documentation for people who are running in Python and calling C++ functions and objects and classes within certain portions of their code, but they also have that other direction. You can also run Python code and run C++ code and call Python. I don't have a lot of experience with using PyBind. We did look into it. I have some Hello World examples, mainly because a lot of my requirements with the Python C API is essentially, it boils down to data transfer, and that's pretty much it. So once with the C API, data transfer is easy. I don't really see myself at this point in time for any of my research needing to, say, declare an object or a class in C++ and use that class in Python. You see, So that's something where PyBind might make things much easier than the current API. So if you want interoperability, not just in the sense of exchange data and then have both of these things work independently, but also like you want to exchange for example, in one of those arguments that you use to send information to Python or back from Python to C++, you send an object that is then available to C++ to actually utilize, right? So an object might have, functions within it. So you just send the function to C++ from Python, and the C++ is able to use that function. So it's a lot more versatile, I would say is the right word. You can do all these things even using the C API, but it's probably going to be a bigger headache. And PyBind, it's kind of wrapped together nicely and with a lot of documentation. So yeah, that's the main difference I've seen so far. I will stop sharing my screen. Any other questions? Someone want me to go through any steps once again, any explanation of the code that was not crystal clear? It's be a good time. Okay, so Maruti says, can we use PyBind for Fortran code as well? So that is a good question. We have some examples of calling Python from Fortran. I see Aaron Huxford said that you can use 4Py. 4Py is basically doing what we did. They put it on the GitHub, but what we did and what they are doing is they have ISOC bindings from C++ to C and from C to Fortran. So once you have that link made from Fortran to C, then you can just easily do what we did right now and call Python. So I was able to actually have an example where we had our main function in Fortran. We imported a module that was in C++. To import a module in Fortran module, sorry, not a Python module. To import the Fortran module, we had to build these bindings. And then once that was done, the C++ module, the C++ class object that we were basically importing just had these calls to Python within it. So we were able to do some really interesting things like, run a case or run any type of simulation in Fortran and then use matplotlib for visualization, which is pretty far out if you think about it. So yeah, but 4Py, which is on GitHub, is a good resource for that as well.
Thank you so much.
Mm-hmm. So Maruti, you said that you had some issues running Cmake in the virtual environment. Was that solved?
Yeah, yes.
Okay.
I installed that. I did not install the scikit-learn and matplotlib. That was the thing that was causing the error. So I fixed that up.
Okay.
Yeah, it works for me now.
Okay, thanks.
If you have time, can you quickly go through the ML model, the ML, what is that? Sorry, the ML module, the LSTM architecture.
Oh, sure, absolutely. Yeah, let me share my screen again. Okay. So this is the Python module. So from the Python module, we will call an ML module. All right. So the ML module is basically like your, your standard sort of Python script that you want to call in from, say, another Python script that has the main function in it, right? So the architecture that you wanted information about is basically an LSTM. So now you can define an LSTM using 5 lines of the TensorFlow Keras functional API. Over here, I decided to subclass a model just to give myself a little more flexibility in terms of how I'd want to, for example, do my batching, how, for example, I'd want to define my architecture and things like that. If I want to do something, if I want to play around with something. So this is what I call it, a standard LSTM. So over here, when we call this model, we have to, for example, give it some data when we instantiate the model. And then this data is pre-processed to lie within a certain range so that training is easier, correct? And then these lines over here basically generate my training data for me. So the way the LSTM works is it takes a window of information, right? And then predicts the next point. And then it does it in a sliding fashion. So it will take 0 to 4, predict 5. Then it'll take 1 to 5, where 5 is now coming from the prediction, predict 6. Then it'll take 2 to 6, where 5 and 6 are now predictions. So you can see how error might grow over time, right? So that's one of the sort of like a research area, when it comes to how you can stably predict results using such recurrent type neural networks. Okay, so we have done some work on that. So we do some shuffling to make sure that the data is randomized, and this is like basics. Splitting, training, testing, splitting. We want to train our data. We want to have a separate training data from a validation data. The validation data is used for early stopping. So when we are training, we don't want to overfit on the training data, right? And the testing data was the data that we sort of got rid of early on within the Python module. So over here, we did get rid of a test data that we will never see. And whatever we are doing now is happening on the train data. And over here, I use the TF Keras layer definitions of the LSTMs to set up my architecture, right? I have a certain initializer. These are all things that you have to play around with and to see if you can improve your performance, obviously. And so when you subclass a TF Keras model, you have to implement a call function. You have to implement a function to train the model. And so that's what I've done over here. So I call my model, I get a certain loss. I use gradient tape in TensorFlow 2, which is a very useful functionality for doing lots of interesting things with the gradients of a network with respect to the input, of the output with respect to the input. And using this gradient, I basically, I perform my optimization step. Okay, so I get the gradient and then I apply the gradients on my trainable variables. Okay, so and then what I do in the train model function is I just scan my entire data set 10 times, and for each scan I have multiple gradient updates. So I have batches, and then batches go into epochs. So each batch I do a gradient update. And if I have, say, 20 batches, so I do 200 gradient updates to train the network. And you can see with the what I predict outside is the validation R squared error, and that improves over time. But let this be a cautionary tale to you. Just because you do well on the training and validation does not mean you will do well on the testing, because the testing might be coming from a completely different distribution, could be a completely different problem, and which is something that you're seeing over here, correct? So then you get some accuracy on your test. Well, in this case, what have I defined to be my test data? Let's see. Okay, so I also have a separate test from the training data that I had. This is just because I copied a previous model that I had. So there are like 2 test data over here. The initial one that I take the training that I had and I generate a 10% slice of that for testing. and then the actual deployment, which is a completely different testing. So so all these are very standard. There's multiple resources online for actually using this. So yep. So that's kind of what it is. Any specific questions about this model?
Yeah, I don't have any. I think now I understand that. Quick question. So this one, the ML module for the theta KNL and the theta GPU is the same, right? And where are you using the, like, are you using a device, like
No,
device?
No, it's not like PyTorch in that sense. I mean, someone else can chip in over there. But in my case, TensorFlow is automatically able to detect the GPU. So
Okay.
So let me see if I can pull up the Python module where I did not have to make any specific changes, but it was using the GPU.
Okay.
So so for example, these parallelism threads, these are just best recommendations from Huiho in data science for threading TensorFlow. So I haven't changed those. Okay. Put a lot of work into finding the right combinations. Yeah.
Okay.
Yeah.
Quick question relating to the yesterday's presentation. You talked about deep hyper to look for the parameter space, right? So can we also embed deep hyper into this?
Can you also embed deep hyper into a C++ code?
Like you have the C++ code calling the Python module, right? The Python module is constructing the standard LSTM. So you can use either Horvath or, like, if you have a large data, you can use either Horvath or like to train the parameters or to find the architecture you want to find. You can use deep hyper there. So
well, I don't know about deep hyper because yeah, I probably want to think about it a little bit more before saying yes or no. But what we have recently done has, and we have not talked about it here in the mini app, is we have the ability to basically share the MPI communicator between C++ and the Python module. So let's say you're running OpenFOAM on 32 ranks. So obviously you will use MPI run for that, right? And so this MPI communicator, previously, the way we used Python was that each rank would start its own Python interpreter, and the Python interpreter would do something, right? But there was a limitation in that the Python interpreter could not talk to each other. Right? So the Python interpreter of one rank cannot talk to the Python interpreter of another rank. It could just talk to its own C++. So if you ever wanted to send information from one Python interpreter to another, you'd have to first send it to C++, correct? C++ would have had to use MPI to send it to a different target rank, and then you would have to go to Python from that. But now we've recently, and by recently it's like less than a week or so, we have recently implemented some examples where the MPI communicator that's initialized using MPI init in C++ is available to Python. So Python now can use the same MPI communicator, but not have to go to C or C++ to send data to another physical location. So it can just communicate with another Python interpreter automatically using MPI for Py. So now we're still exploring this, but that gives us a lot of possibilities of actually using Horvath, which uses MPI, right? For training while a simulation is running. So you can think of a simulation running, then whatever rank 0 is, rank 0 can use the same MPI communicator to also control like a Horvath training. I'm not experienced in Horvath. I haven't used it enough, but I can totally see that being something worth looking at.
Okay, makes sense. Thank you.